Hi everyone. In today's lecture, we will discuss about the impulse response of parallel and series LC network. So, in the parallel LC network, I'll assume current as an input and voltage across the capacitor or the inductor as the output. And in the series LC network, we'll be applying voltage as an input and we'll be measuring the current flowing through both the inductor and the capacitor as the output variable. So II, I'm just using II V0 in small letters as the voltages and currents in time domain, and in capital letters, capital V0 and II will represent the Laplacian variables. So first, before we solve this problem, very quickly I'll just try to give an intuitive explanation or intuitive representation of a parallel LC circuit and a series LC circuit using the block diagrams. Okay. So first, if you look at this first circuit, that is the parallel LC circuit, the input current splits into IL and IC. I can also look at it as a feedback system. Imagine there was no IL. So then the entire input current would have fully flown through the capacitor. Now had there been no inductor, the entire II would have forever flown through the capacitor and it would have just looped back. But because there is a capacitor, because there is an inductor, the capacitor will start developing a voltage across it, and this voltage will in turn generate a current IL, and that current IL is going to reduce the current that's actually going into IC. So there is some kind of a feedback action here. So we'll try to draw the feedback mechanisms here. So first I'm going to assume that there was only a capacitor. So then if you feed IC as an input to a capacitor, so I'm going to use Laplacian variable capital IC. So this is in time domain. So if I take Laplace transform on both the sides, I will get IL plus IC. So IC is by 1 by SC, the impedance of the capacitance. You are going to get voltage V0 at the output. This voltage generates a current through the inductor. If you divide the impedance of the inductor, what is 1 by SL, you will get the current, which is IL. This current is going to subtract from the input current, and it's eventually going to flow through the capacitor. It's going to reduce the current that's going to flow through the capacitor. So now if you look at this, I have represented the parallel LC circuit as a feedback system. Now this feedback system, the loop gain LFS, is nothing but the product of the forward path and the feedback path gain. That will be 1 by S square LC. So I'm going to use omega naught square as, going to call omega naught square as 1 by LC, where omega naught is 1 by root LC. So this can be written as omega naught square by S square. Now this system, the loop gain here, if I try to plot its poles, open loop poles, it has two poles at DC, right? I'm just going to equate this S equal to 0, it has two poles at DC. Now once you close the loop, then the root locus of this system is going to be on the j omega axis. Okay. Now to find the closed loop poles, you have to just equate the loop gain to 0. I mean 1 plus loop gain to 0, and then you can show that it is simply S equals plus minus j omega naught. So once you close the loop, the poles will, this is the open loop poles. In the closed loop, the poles will move to, they will move along this direction, and it will come to minus j omega naught and plus j omega naught. So you'll actually have two purely imaginary poles. And we know that for any system with imaginary poles, the transfer function is actually going to blow up to infinity at omega naught, and again which is consistent with our the resonant frequency. Okay. Now there is something that I didn't mention in the last class, that any resonance system, the simplest resonance system is a second order system of this form. You can write it in this form in time domain as d square y by dt square 1 by omega naught square plus y equals some k times x. In fact, you can even have derivatives of x. It doesn't matter. You can have derivatives of x. So the equation should be of this form. You need to have at least a second order term in y. This is the lowest order resonance system, and a proportional term in y and no other term. Okay. You can also have higher order systems, higher order resonance systems. Okay, but this is the simplest second order system. Now the LC circuit here, we know the transfer function. From this I can actually write the transfer function for this circuit as V0 upon II will be SL by 1 plus S square LC. Now I want to write this entirely in terms of omega naught. So I'll replace LC by 1 by omega naught square, and this term will reduce to S by S square plus omega naught square. Uh, so I'll take LC is 1 by omega naught square. If you substitute it, you'll actually get omega naught square into L. So again, using omega naught as 1 by LC, I can reduce this as omega naught square as 1 by LC. This will be 1 by C S upon S square plus omega naught square. So this is the transfer function you get. Okay. Or first, I just wanted to show the second order differential equation from this equation directly. We'll use this result later. So if I want to write this in time domain, this expression here in time domain, that will be simply d square v naught by dt square, okay, into LC plus v naught equals L dii by dt. Okay, so this is your simple second order differential equation, and that matches with actually what we already what we said that a simple second order resonance system should follow. Okay, so in fact here I'm actually, this is not a purely resonance system. I mean, the word resonance is even used for systems with losses. I'll come to that probably in the next lectures, but here I'm referring to systems with infinite gain at the resonant frequency. So that's what I'm referring to, and for those systems you should not have any term other than the second order and the proportional term. You should not have any other term. Okay, so in the upcoming lectures, you will actually see that we can also have a first order derivative, and that will model that when you have losses in circuit, you'll also have a first order term. But in this lecture, we are focused on purely lossless circuits where the gain at the resonant frequency is infinity. Okay. Normally it will be very high. In practice, every circuit has some losses, so it will be very high. It won't be infinity. But here we are analyzing an ideal lossless circuit. Okay, so I'll go back to the transfer function, which is actually V naught by II for this system is 1 by C S by S square plus omega naught square. So this is the transfer function for the parallel LC circuit. Okay. Now similarly, for a series LC circuit, you have voltage as an input and capacitor and inductor. So in this circuit, what I am going to do is, usually let's assume that I am going to apply a sudden input, then most of the voltage will appear across the inductor. I am going to call it as VL of t. Then that is going to generate a current in the circuit called I naught of t, which then is going to develop a voltage across the capacitor Vc of t. That voltage will then reduce the voltage across the inductor. So there is again some kind of a feedback mechanism. Okay, and which in turn, when you reduce the voltage, you will also change the current I naught of t. So there is some kind of feedback mechanism. So we will try to draw that. So here, as I said, first here we will apply inductor. Inductor is the model that we are interested in, and the output variable here is current. So first, the inductor voltage VL of t, input is fully going to appear across this in the open loop. Then the current through the inductor is 1 by SL. Okay, I'll actually use the Laplacian variables. So it is V capital L. And in writing a KVL in this loop, we can simply write Vi of t equals VL plus Vc. Vi. So I'll have capital Vi equals capital VL plus capital Vc. So this is your Vi. Now this voltage, the current through the inductor, when it flows through the capacitor and the impedance is 1 by Sc, it's going to create a voltage drop of Vc, which then subtracts from the input voltage, which will reduce the inductor voltage. Okay, so now again we have reduced this to a simple second order, simple feedback system. Again the same system, it has the same loop gain as the previous system, which is omega naught square by S square, and the poles, it has two poles in the closed loop at plus minus j omega naught. In open loop it has two poles at 0. Again this is a resonance system with a gain of infinity at omega naught. Okay, so this system, we just described this as a feedback system, a series LC network also as a feedback system. So here voltage is input and I naught of t, current is the output. Now the transfer function for this circuit can be very easily shown as I naught upon Vi will be Sc by 1 plus S square LC. Okay, so I can also rewrite this in terms of omega naught square as 1 by L S by S square plus omega naught square. So this is the transfer function for a series LC circuit where voltage is the input and current is the output. Okay, so now here I'll just write two popularly encountered Laplace transforms of signals which we encounter popularly, which is one is impulse. The Laplace transform of impulse is 1. The Laplace transform of a step function is 1 by S. And the Laplace transform of a sinusoid, so for example cos omega naught t into u of t, I'm going to multiply the u of t, then the Laplace transform of this is S by S square plus omega naught square, and sine omega naught t, sinusoid with a sine, I mean it's a sine wave which starts from 0 t equal to 0, that will be omega naught by S square plus omega naught square. If you just remember these results, it comes handy when we are analyzing for different frequency inputs. So using this, I am going to apply first for a parallel LC network I am actually going to apply a current input. As I said, for current, if it's an impulse input, I'll assume it's a charge. So Q into delta of t is the input, and that is fed to an parallel LC network, and voltage is taken as an output. And we showed that the transfer function for this circuit was 1 by C into S by S square plus omega naught square. Now if I feed an impulse to this, so this is your transfer function H of S, the output variable V naught of S is simply going to be transfer function multiplied by the Laplace transform of the input variable, which will be Q by C. The Laplace transform of Q into delta of t is just 1, is Q, right? Laplace transform of delta of t is 1, so you get Q. So Q by C into S upon S square plus omega naught square. Now if you look at this, I can find inverse Laplace transform and write V naught of t as Q by C cos omega naught t into u of t. So this is the expression we get by taking inverse Laplace transform of this equation. So it is nothing but a sinusoid of amplitude Q naught by C, and it's an everlasting sinusoid. It never decays down. It persists forever, and that should make sense because, for example, if I have an inductor and a capacitor, and you are giving a sudden impulse of current, now inductor is going to offer infinite impedance. We know that at sudden changes, so all the current will fully flow through the capacitor. Since the current is an impulse, it's going to immediately develop a step voltage across the capacitor, and that voltage at t equal to 0 plus is going to be Q by C. Now we know once a resonant circuit starts, parallel LC circuit starts from an initial voltage of Q by C, it's going to be discharged by the inductor. Energy in the inductor will be peak at this point. We have already discussed that extensively in the previous lecture. Then it's going to be a sinusoid like this. It's going to continue. Okay, and that's what is written as an equation here. So what I did just now was a time domain way of looking at it, and we get the same thing from you also going from a Laplacian domain. Now we'll try to see purely from a frequency domain, does this output make sense, or we'll try to draw intuitions purely from frequency domain. So first I'll consider the function impulse, which is Q into delta of t. Now the Fourier transform of Q into delta of t is a constant, which is Q, which means it has same energy at all the frequencies. Now we will try to plot what we call power spectral density. Okay, it's a very useful way of visualizing. For example, sinusoids, and most sinusoids are power signals. Okay, their energy is infinity and they are power signals. Now how do you find power from Fourier transform? You just square the Fourier transform, so you would actually get Q square. So I'll actually ignore Q for the time being. I just want to explain it for an impulse. So Q is just a scaling factor, it shouldn't matter. When you square it, you will again get the same value. It is 1, 1 square is 1. Now if I ask you to find power at any single frequency, it is 0. Okay, this, I mean, because it's a spectral density. So if I ask you to find power in a certain range of frequencies, say the width of the frequencies is delta f, then if the amplitude is 1, the power contained in that is 1 into delta f. Okay, in this band. So if I make delta f 0, if I am trying to ask you to find energy at a single frequency, then I am actually making delta f as 0. Then the power contained will actually tend to 0. So actually it doesn't have power at a single frequency. Then how does it actually generate? See, you are feeding an input which doesn't have a finite power at a single frequency, but the output is actually a sine wave, and we know the Fourier transform of a sine wave is an impulse at f naught. Okay, and we already discussed that for a sinusoid, even though it exists only for one interval, one instant, the impulse exists for one instant, it integrates out to a finite value. If I find the area under this, it's going to be a finite value. So that's how we represent power signals using Fourier transforms, by using impulses. Okay, so if we assume an existence, I mean using impulses, we can actually represent power signals which are sinusoidal signals. So then how does, the question is, the input doesn't have finite power, but how does the output have a finite power? In fact, the input has 0 power at f naught, at f naught itself. So the answer lies in the fact that the transfer function of this system, so I'll actually write the transfer function. The transfer function of the system, if you see, it is actually SL by 1 plus S square LC, which is nothing but j omega L by 1 minus omega square LC, or f square by 2 pi LC. You can write it as 2 pi square and all that. Omega is 2 pi f, you can write it in terms of f. Now we can see that at omega equal to 1 by root LC, the transfer function blows up to infinity. So actually the transfer function here blows up to infinity at f naught. So intuitively you can see that at every other frequency, the transfer function is finite. Only at f naught the transfer function is infinity. Okay, so when you multiply that with a nearly 0 power signal, you can visualize that you might get some finite value, finite power at that frequency. Because everywhere else the value is very high, even though it's very high, the input has 0 power there. So you really need an infinite gain to give you some power at that frequency f naught. So that's why you're actually, intuitively you can see that you're getting an impulse or you're getting a finite power signal. It's because your system gain is infinity at that frequency. Okay, so that's why you're getting only sinusoid as an output. For every other signal the gain is very low, so there is no output, there is no you don't get you're not getting tones at other frequencies. That's what I mean by this explanation. So even though the energy level or the power contained in that frequency is 0 and in the input signal, because the transfer function has infinite gain at that frequency, you are actually able to get a finite power output signal. Okay, so that's the point I was trying to convey. So now the next input, I thought I'll also give a small intuition for an impulse. How do you actually get an impulse? Why does the Fourier transform of an impulse is constant? The Fourier transform of an impulse, we said, is constant for all frequencies. Now we know the Fourier transform is nothing but a sum of complex exponentials, right? It's nothing but, you can visualize this as e power j pi to 2 pi j 2 pi f t naught, f k t naught. I mean, if it is e power j 2 pi k f naught into t. Okay, this is I can write it as a Fourier series expansion, and then I'll just make f naught tend to 0. Okay, in the limit, then you would get a representation of an impulse. Okay, here this is actually assuming that there is some kind of repetition. I have written it for this. We'll discuss impulse train, I'll come to that, but I just wanted to show that Fourier transform is nothing but you're representing your input signal using a bunch of sinusoids. But for an impulse, you have sinusoids complex, like e power j omega t is a sinusoid, e power j 2 pi f t is it's a complex sinusoid. We are taking f from 0 to infinity, in fact minus infinity to infinity, and adding them up, all the sine waves with same amplitude. Okay, then we are saying you actually get an impulse. Now how is that true? Why is that true? So what I'll do is I'll just take, for example, e power j 2 pi ft. It's a complex exponential. So now the best way to understand complex exponentials is to use the phasor diagram. Okay. So we'll see each frequency. There are multitude of frequencies in this signal. I mean, in fact, it's actually a set of signals which we are adding up to form the impulse. At t equal to 0, this is a complex plane. This is the real part, and this is the imaginary part. I'm trying to plot the sine wave. Now, since the magnitude of all the sine waves is 1, so all the points at any given time, they are all going to lie on the circle whose magnitude is just 1. The magnitude is the mod of r is going to be 1. This is a complex plane. R e power j theta is going to be the representation. So first at t equal to 0, all the sine waves are all going to start from here. All the sine complex exponentials will all start from here. Okay. Every complex exponential at t equal to 0, e power j0 is going to be 1. All the infinite sine waves, every sine wave is going to start from here. So they will all add up together and you will have an infinite value at t equal to 0. Now I'm going to slightly move away from t, which is t greater than 0. After that, a low frequency sinusoid, for example, would have advanced, say, by an angle theta. Since there are so many sinusoids of very high frequencies, some other sinusoid would have advanced by an angle which is exactly opposite to this, almost 180 degrees away from this. Okay, then the resultant sum of these two, we are actually adding up all the sinusoids. That's how you get the Fourier transform. The resultant of this, it will cancel out this. The resultant is going to cancel out. So which means for any t greater than 0, you are just adding up a bunch of sinusoids, complex exponentials, with different phases. Since there are infinite of them, we can actually, in fact, we can prove this as well. Every sinusoid will cancel out. Every sinusoid will actually add destructively because all the amplitudes are same. For every angle theta, you can always find some other signal which has advanced by pi plus theta. So these two will exactly cancel out. If I'm going to do a phasor vector sum of this vector and this signal, then you are going to get 0. So that's why for any value t greater than 0, which or t not equal to 0, you will get 0 as an output, and only at t equal to 0, all the sinusoids will add up and you will get a huge value. So that's how impulse is generated using a sum of sinusoids. You can also visualize them as a lot of cosine signals. I'm just adding up a lot of cosine signals with different frequencies. Everything will blow up at origin and everywhere else it will add destructively. Okay, yeah. So that's the intuition for Fourier series for an impulse function. Now we'll come to the main problem, which is actually I'm going to feed a train of impulses to the system. So first I'll feed an impulse of 1, charge q. Second impulse I'm going to feed a t with the same charge, and so on. Now how will the output across the parallel LC tank look like? Okay, so here I am feeding a train of impulses. Okay, now how will the output look like? And you should understand the periodicity of this. In this example, I am going to assume that the periodicity t is 2 pi by omega naught or 1 by f naught. It's exactly at the resonant frequency. The periodicity of this impulse train is same as the resonant frequency. Now first, the instant I am applying an impulse of charge at t equal to 0, we know that the waveform is going to look like this. First it will start at q by c, and then the output is going to be a sine wave. It's going to keep oscillating. But here at t, which is 1 by f naught, we are going to inject another impulse. Now here at this point, the capacitor is now, say initially what would have happened when the capacitor is charged to a voltage q by c, it would have discharged all its energy here, and inductor would be fully storing its energy. Again here capacitor will again store its energy but in the opposite direction. At this point inductor will store its all the energy in the system. Now back here when when we return back to this point, when I'm returning back to this point, capacitor now is fully charged to q by c and it's storing all the energy. Now when you're injecting another impulse at t, what's going to happen is the amplitude is now going to double, because you already have a charge which is q on it. Now you are going to dump another q amount of charge on the capacitor, because instantly when you transfer an impulse, the entire current will flow through the capacitor and the capacitor will develop that voltage. This is going to go to 2q by c. So now this is this waveform, but remember the frequency is same. I mean it's as though the system is again started at a new value which is 2q by c. Frequency doesn't, that's determined only by L and C. Okay, that is the same. So it will have come to 2q by c. Now at 2t I am again going to inject another impulse of charge q. So then at that point your output is going to go, suddenly it's going to jump to 3q by c, because you are adding another charge. The capacitor now it's going to have 2q amount of charge at this point, and again I'm sorry. So again you are going to add charge to this capacitor, so the voltage will go to 3q by c. So what's happening here is the voltage across the tank is increasing linearly. Okay, eventually at t equal to infinity, the amplitude will go to blow up to infinity. So that's what is happening in the system. So mathematically, for example, if I can write a sinusoid q by c cos omega naught t, I'm going to multiply this by p t of t. P t of t is a pulse signal which exists from 0 to t seconds and with an amplitude of 1. Now to represent the signal in the second half, I have to use q by c cos of omega naught into t minus t. I've shifted it by t seconds, and pulse is also shifted by t seconds, t minus t. This is actually 2q by c. Okay, so in the same way, for the kth cycle, when t is kt, this is going to be k plus 1 into q by c cos of omega naught t minus kt into pt of t minus kt. So you can see the amplitude of the sine wave also has it keeps on increasing. Okay, it keeps on increasing linearly. So if I write a general expression, it's going to be summed over k going from 0 till infinity. You would actually have kq by c cos of omega naught t minus kt into pt of t minus kt. Okay, so this is the expression for the general expression when you feed a periodic impulse train to this system. Again, this is the expression from time domain. So we'll try to analyze the same thing from frequency domain point of view. Okay, so what does this tell you is that as t goes to infinity for a very long time, at that time k will tend to infinity, your output is going to blow up. I mean, you are going to get an infinite output. You are going to get a sinusoid, but the amplitude of the sinusoid is going to be infinity. So the power is also going to blow up to infinity. Okay, so we'll try to give an intuitive reasoning in frequency domain. So first, we know the Fourier transform of an impulse is a constant. Now what I'll do is I'm going to repeat this impulse function periodically in time, 0 t for every t seconds, 2t and so on. I'm going to repeat this. Then what happens to the Fourier transform is it gets sampled in frequency domain. Again, this is a very standard theorem in signals and systems. So when you introduce sampling in one domain, when you sample your signal in time domain, your frequency domain becomes periodic. So similarly, if I introduce periodicity in time domain, frequency domain becomes sampled. I mean, all it means is that, what I mean when I say frequency domain is sampled, it's just that you can always have frequencies only at certain values. I mean, it's a periodic signal, so it can contain energies only at those frequencies of the fundamental period or the fundamental frequency. So when I sample this, I mean when I make it periodic in time domain, you have to sample this function using impulses. So you'll be having impulses in frequency domain, and the spacing between the impulses is 1 by the periodicity in time domain. So that will be f naught in this case. In fact, the amplitude of this can be shown to be 1 by t. I'm not doing that now. You can simply do a Fourier series representation. You will get this result. So this signal has same energy at all the multiples of f naught. Now we know that if I feed a signal with some finite energy, you're going to get a finite power, right? Even if it has no power, at that frequency we were getting a finite power because of the gain being infinity. Now if I pass this signal through a transfer function which literally blows up to infinity at f naught, then what would happen is that intuitively you can see that you are actually going to get an impulse of infinite magnitude. In the steady state you should in theory get an impulse of infinite magnitude. So which is again uh, explains the power itself is infinity. Even though if I try to integrate this impulse, although the amplitude of the impulse itself is the weightage of the weight of the impulse itself is infinity. So it's going to integrate out to a finite, into an infinite power, and that's what is shown in this equation as well. The sinusoid with a linearly increasing amplitude. So when I feed impulse train, that's the output you're going to get. Okay. So I think with this I'll just stop this lecture now. In the next lecture we will start discussing about pulse response. Sorry, pulse response of LC circuit. First, the second order LC circuits, both series and parallel. I haven't analyzed it for series circuits, but it's exactly the same analysis for series LC circuit, because the transfer function where we give voltage as input and measure the current as an output, you are going to get exactly the same output for a series LC circuit as well. One thing you can try out is what happens when I feed a signal like this. So I'm going to invert the impulse sign every t seconds. Okay, so you can actually try and see how will the waveform look like, and for your own understanding you can actually try and give an intuitive reasoning for the same. Okay, so I'll stop at this point.